Sorry.
No, I just wanted to make sure that I can share my screen, that's all.
Pepe tornerà. Okay.
Hello, everyone. Welcome for this RoboLaunch session today with Alex Foessel. Dr. Foessel is an internationally recognized expert in off-road automation. He worked for John Deere for 18 years in roles like Director of Technology Innovation, Director of Customer Support, and Lead Architecture of Automation and Autonomy. In 2020, Alex founded Balanced Engineering, a consulting training and engineering services company focused on architecture, product safety, and commercialization of highly automated off-road equipment with customers in agriculture, construction, marine in the Americas, and Europe. Alex and his family continue to raise Angus cattle in Chilean Patagonia. Alex obtained his PhD in robotics at Carnegie Mellon University. So, uh, without so, Rachel, do you have a few words to say to us?
Thank you so much, Leo. My name is Rachel Burson, and I want to welcome you to a special session offered by Carnegie Mellon University. This initiative is bringing our strength in robotics and AI and bringing these conversations and connecting communities across the world. And we have a very special focus over the month of December, where we're connecting with friends and colleagues in Latin America. And I'd like to thank the U.S. Embassy in Chile, Santiago, for their support in sharing this and helping to build really an ecosystem so that we can work together on some of the complex challenges that are facing all of us. I'd like to welcome Claudia Carrillo from Education USA to say a few words.
Leonardo, you may need to enable her.
Yes.
camera.
All right, so I can speak, but I don't have control over the camera. So
Yeah, you should be able to turn on your camera now.
okay, let me see. There you go. I think so. There I am. Okay, thank you, Leo.
No problem.
So very nice to meet you all. Very nice to see you again, Rachel, Dr. Foessel. A pleasure. Thank you so much for having us here today. I mean, very briefly, my name is Claudia Carrillo, and I'm the advisor in Education USA in Santiago, Chile. And Rachel asked me to do it in Spanish a little bit, so en español. Entonces, bueno, estamos en la oficina en Santiago, tenemos varios centros en Chile. Y para quienes no nos conocen, Education USA es un programa del Departamento de Estado de Estados Unidos que se dedica a asesorar a los estudiantes en toda la postulación a las universidades acreditadas en Estados Unidos. A todas, entonces no tenemos ningún convenio en particular con ninguna, sino que más bien tratamos de ayudarlos a guiarlos, ¿no es cierto?, en cuáles serían las mejores opciones para ellos según el perfil de cada uno. Tenemos varios programas, todos gratis, que pueden postular los estudiantes cada año. Ahora mismo tenemos el programa abierto, el de Fondo Oportunidad, y el Competitive College Club, que están abiertas las postulaciones para los estudiantes de tercero medio en Chile, para que todo el próximo año se dediquen y les ayudemos en todo el proceso para postular e irse a Estados Unidos en el 2025. Para más información y cualquier pregunta, los invitamos a visitar nuestro sitio web, que es www.educationusa.cl, ¿sí? Y el sitio web de Education USA mundial es educationusa.state.gov. Y eso, cualquier pregunta, estamos aquí para ustedes.
Muchas gracias, Claudia. Un gusto conocerte.
Muchas gracias, igualmente.
So the interesting thing is that today I'm calling from Chile as well, but in Patagonia, further south from where Claudia is located in Santiago.
Qué lindo.
Well, thank you very much, Claudia, for being here. And well, now without further ado, I'll hand it over to Alex.
Right, and while I set up the presentation, what I would like to also is introduce Dave. Dave Carnegie is an intern at Balance Engineering. Balance Engineering is a company founded in, incorporated in Iowa, but with also locations in Pittsburgh as well as in Brazil. Dave, if you can say a couple of words about you, because you're going to be my co-presenter, then we'll get going with the presentation.
So as Alex mentioned, I'm an engineering intern at Balance Engineering, and I'm a junior in electrical and computer engineering at Carnegie Mellon. So I'm really excited with the work that I've done with Alex and the work that I'll do in the future.
Thank you, Dave. And let me just get this started. So today the topic is going to be a very, very interesting one in the sense that it is about robotics, and it is also about bringing robotics to the market. And one of the key factors that are going to be and will continue being very critical to be successful bringing technology to product to a business is safety. So we're going to be presenting today a few elements of how you bring safety into a robot so that it becomes a safe tool for people. We're going to focus most of the work around agriculture. That is the area where we know the most, but some of the lessons learned and some of the insights are also applicable to other robots, whether it's on-road and off-road. The topic, the presentation is going to go through a few things, but just before I go through the agenda, I wanted to show you, this came up my inbox not too long ago. Look at this. It's an article that says Ag Robot Buying Guide 2024 is out now. What I'm trying to say with this is that even though often we think of robotics as something of the future, in the case of agriculture, is something that is existing today. And we're going to be talking about, agriculture, also talking about how mining, how construction and turf are adopting robotic technology today. And this advertisement is an indication of how that is indeed happening. We're also going to talk briefly about academia, and I'm going to just give you a couple of examples of work that relate to my prior work as a robotics graduate student at Carnegie Mellon, but then some of the challenges of bringing that technology to become a business with sustainable profits. Then the question is, how do we know that a robot is acceptably safe? And then we're going to be talking in how we're taking some key elements of the safety case that is being built for on-road to off-road. We're going to highlight some standards, aspects of risk assessments, implementation in practice, and then some of the key challenges ahead. This is something that is going to be a very fertile research field in the future, and also it's a very interesting specialization opportunity for early career professionals. So this is a powerful machine. You can see that this is a tractor, probably between 3 to 100 horsepower, that is pulling this 10 chisel plow and is working the soil. This tractor has no operator, and like this tractor, there are many machines around from different brands, John Deere, AGCO, and others. And the question that we need to be thinking about is, how do we know that this machine is going to be safe, especially when it's so powerful and it's going so fast? There are some alternative ways to do robotics for agriculture. This is an example that is coming actually from Brazil. It's designed and built in Brazil, and you can see that it's a vehicle much slower, but also is doing the application and is run by solar power. So as opposed to the tractor that requires to be refueled every so often, this actually can run over and over and over, and with its battery system can continue the operation even at night. So that's a very different type of robot, but as you can see, there are many different things. But all those two examples had no people. Now look at this company from Philadelphia in Pennsylvania. This company is called Burrow, and the vehicle is meant to be a helper for people who are harvesting different types of fruits. You can see that those are blueberries. So then instead of people just going back and forth with trays or pushing a cart with trays with fruit, this machine goes to the field with empty trays. Then the laborers are going to be emptying those, unloading and loading the new trays with fruit. Well, now we're talking of a robot that requires significant safety, because if there's an accident, then no one is going to be happy, nor the person that suffers the accident, or the rest of the workers, or OSHA, or any other of the US government that are regulating the safety in these operations. So this leads us to the following very key and important element of taking robotics technology to the market. And that is, what is acceptably safe? This text was taken from the John Deere 2022 Sustainability Linked Bond Framework. You see that that is available, is public information, but what I would like to highlight is that for a business like John Deere to bring technology into products and to the market, it needs to be able to adhere to this. And look in the center paragraph, the general rule for product safety, which is a legal element in the USA. This rule requires that an acceptable design must not present an unreasonable risk of injury to a product user or others nearby. In applying this rule, we consider the people, environmental conditions, and other products with which a product is likely to be involved. The reason why this is so important is that, first of all, when you consider this rule for product safety, you're going to be paying a lot of attention to potential risks from the beginning of your development all the way to when you sell and commercialize a product. At the same time, if you do things well, and if ever something goes wrong, you are going to be able to show that you have thought about safety and that you were not negligent. So then you have a better chance to actually win a lawsuit in court. So when a business thinks about bringing robots to the market, is thinking first, we need to create a safe product, but also it has to be documented and demonstrably that you can demonstrate that you did indeed apply best practices in industry in case you ever you have to argue that your design is indeed safe. Let me go back to 20 years ago. And the reason I mentioned this is because this talk is about lessons learned not only in industry, but also in academia. I'm going to just, on the right side, there is a figure that came from my thesis, my PhD thesis back in 2002, scene modeling from motion-free radar sensing. At the time, most of my focus was to demonstrate that by using certain algorithms, I could build a representation of the environment using radar. And it was all about focusing on the principles, on the math, on the statistics, and showing that is possible. From there, and I went to work in a John Deere, a global well-known ag equipment producer. And you can see that those topics were actually eventually put into a patent. And then, moreover, we put those concepts to work in a stadium mower. And you can see this machine that is actually turning and avoiding and slowing down close to the goal post using these algorithms. The problem is not always these prototypes make it to the market. And the question is why? And the main lesson for me is that we did not put formal attention to safety. Of course, we did put attention to safety, but we did not put formal attention to safety that actually could be communicated in company and communicated to liability attorneys in a way that they could actually measure the risk for the company. But let me stop that and show you that then it is possible to actually do that. And here's an example of a product that did go to the market. It's a simpler design. It's a lawnmower for gardens, has basic technology, but we work to meet the standards and regulations in the European Union. It had a great safety track record over a decade, and it was sold by thousands of machines per year in all Western Europe. So I just wanted to show you that the trajectory from concepts as a PhD all the way to product exists, but sometimes it's longer and more painful. And today we want to show you how to make it shorter. Dave, do you want to cover this slide, please?
Yes. Okay, so covering a lot of the topics that Alex has been mentioning earlier, I think that when we're looking at the difference between his work on his PhD thesis and the work at John Deere, it's very apparent that there's differences between the amount of time that might take to bring a product to market when you're thinking about safety in the forefront and before you even start your design, as opposed to when you're thinking of it after the fact. Because if you've already spent time developing something and then you come to realize later that your design is not safe, it'll be very expensive to modify the design, and it'll also take a lot more time to ensure that all of the changes that you've made constitute a safe product. And so we can look at some examples from the on-road autonomy circumstance in order to look at what is the best practices in industry right now. And so with Aurora, we can see, for example, in G5 that it talks about the self-driving enterprise being trustworthy. And so that constitutes, for example, is the company putting safety in the forefront? Do they have a safety culture in their company such that everyone is thinking, how do I make sure that this is safe throughout the engineering process, as opposed to what is the easiest or what is the cheapest way of implementing something. And obviously, when we're looking at implementing safety, there is the balance between having something that's safe, and in this case, what we're looking at is we're trying to make sure that something is minimizing the reasonable amount of risk that we might be facing. So if we look at G3, for example, we see that we're looking specifically at unreasonable risk and what can be resolved. So when we're looking at comparing autonomous performance relative to human-made performance, generally we want to have a margin of safety by 10x. So for example, we want our autonomous solution to be 10 times safer than a human operated vehicle, so that if we made some mistakes in terms of measuring how exactly safe some circumstances, some processes, then we still have a leeway such that our autonomous solution is actually safer than the human operated vehicle. And so when we're looking at this, especially, we want to be looking at where can faults arise. Will our, for example, operating environment be what we expect it to? What can actually happen in the real world? And how can we mitigate the risks that those unexpected circumstances might cause? So Alex, would you mind going to the next slide?
Yes, and I will just make just a quick note that all of these blocks are really to support that top-level claim that Aurora's self-driving vehicles are acceptably safe to operate on public roads. By the way, Aurora Innovation is a company located in Pittsburgh and other cities, and the founder and the CEO is also a robotics PhD graduate from Carnegie Mellon.
So now that we've seen what an ideal use of the safety case in the on-road circumstance looks like, we might need to look at how off-road circumstances differ such that we can't necessarily have a one-to-one transfer of the standards. And so in particular, the risk profiles are extremely different across on-road and off-road autonomy. So for example, when we're looking at roads tend to be pretty flat, whereas when we're looking at farms, they might have differences in elevation that might be difficult for the tractor or vehicle to traverse. Additionally, when we're looking at the on-road circumstances, on highways, for example, there might be few people who are interacting with the road. But when we get to streets, then streets might have more people and pedestrians who are interacting with the environment. And when we're looking at farms, for example, in general, we might have the people who are there are more knowledgeable as to what the tractor is going to do at a given point in time, and might be able to take precautions that people on road might not take. So I think that's enough for this slide.
Very good. So then, as Dave was mentioning, so there are really good frameworks that have been developed for automotive. And the question is, how do we bring them to the world of agriculture? So for that, we need to move from, streets and signs and, driving regulations, et cetera, to farms and soil and wood and crops and tractors, etc. So the context needs to change. And that is something that we at Balanced Engineering are doing, which is working to adapt the language from a safety case that is valid for automotive or on-road and create one that is going to be very specific for agriculture safety, for autonomy. And that also has some of the similar elements like a safety culture, which was mentioned by Dave. There's some other things that is the basic safety, like, just standard placards and signs and protections of hands and covers, etc. But then we go into functional safety, that is really the absence of unreasonable risk due to the hazard caused by malfunction. So if something fails, it needs to fail safe. There's also the safety of intended functionality, an area that is developing very rapidly, because it's really to understand for those safety critical functions like obstacle detection, to what extent we can ensure that the obstacle detection configuration, sensors, processing, algorithms are indeed going to reduce the risk to an acceptable level. Cybersecurity becomes really, really critical. And also we talk about life cycle safety because the product does not need to be safe out of the factory. It needs to be safe throughout its life. So let me go a bit deeper into functional safety and show, for example, that for many of these, there are international standards, like in this case, ISO 25119, which, as you can read on the right, it is specific for tractors and machinery, for agriculture and forestry, for the safety-related parts of the control system. It has 4 parts, and the key thing here is to really manage the risk of harm due to hazard caused by the malfunctioning behavior of a system. And that should be designed to properly handle human errors, systematic errors, hardware failures, and other elements of risk. And the intent of functional safety really is to get to the basic objective of reducing the maximum number of dangerous failure per hour. And you can see, depending on the performance level, we can go from 1 every 10,000 hours. By the way, just to give you an example, a tractor in Brazil that is working in a cane operation is likely going to be working 3,000 hours per year. So in 3 years, it would complete almost 10,000 hours. But this should be done for all of the pieces of the tractors of that type that are in there. So imagine that there could be 1,000 tractors. So if we believe that there's 1,000 tractors and one of them can fail and have a failure that could be dangerous 100 times a year, then we're finding ourselves with a level of danger that is unacceptably high. That's why we continue driving and trying to reach, especially for those functions like steering or braking that are critical to safety, to fail much less frequently. Like, for example, in the case of D, 1 or every 3 million hours of operation, or E, 1 over 10 million hours of operation. So what we're trying to do, and remember when I told you that in the case of my PhD thesis, I was trying to make something to work once and show that it's possible? Well, here we're trying to work to make a product so that that product will never have a failure more than 1 over 10 million hours of operation. So that is what distinguishes a lot from academia and research from actually taking a product to the market, is that in one side, you're trying to show what is possible and show the functionality. And that's really important, because without that, nothing happens. Innovation doesn't happen. But when we're going to be putting machines in large numbers among people, like the lawnmower that I showed you that sold by thousands over a decade, then we want to make sure that we're not exposing those people to an accident more than 1 every 10 million hours of operation. And to accomplish that, we focus very much on the systems engineering. Here's the systems engineering view on the left that is well known by most of you who are in the business of robotics. And what we can see here is that you go start with the requirements, and typically you follow the V. In order to create these very, very safe systems, we almost overlay or overlap another V, which is the one that is going to be looking into risks, hazards, trying to estimate the likelihood of them, and drive the requirements to keep the system acceptably safe throughout the design process. On the right side, you have a V that is focused on software, because this not only affects mechanical, hydraulic, electric, electronic systems, but also, especially nowadays, software. Because software is becoming one of the most critical elements of a system. And for that, when we understand the criticality, then we define what is the software requirement level. This is all expressed in the standard. And then depending on how critical it is, more critical to the right, then what we're seeing is that for some approaches, we can use informal methods. That is the row 1A. That is potentially applicable for software levels that are not as critical. But when we go to software requirement level 3 and 4, informal methods are not appropriate. And we're going to use semi-formal methods to actually design an architecture and test the system. Eventually, we get also to using inspection of software architecture on the column row 3A, where may not be always required for software critical software requirements level 1, but certainly it's going to be in green required for the upper levels. This is an example of how these very extensive international standards are driving the level of rigor to create the architectures and to develop the software as well as some other components. And finally, to make this repeatable, we bring these concepts and we need to integrate them with the product development process. Some of you may be familiar that larger companies standardize product development, and typically they have a process that starts with the ideation of a new product, which is more like the discovery. Then you have a product definition. Eventually you get into prototyping, detailed design, validation testing, and eventually commercialization. This is another way to look at the V, but it's much more focused not just on the design, but also on the productization, etc. Safety needs to be brought in and connected to each one of these product development phases, so that when you're done and you get to commercialize, you know that that product was born, even at the ideation, trying to understand what are the potential hazards and what are the mitigation approaches that the design team is going to use, and eventually that during validation and testing, all of those potential failures are tested so that you can show that the system is not going to fail or is going to be safe, for example, at the level E, 1 over 3 million hours of operation. Dave, do you want to talk the aspects of risk assessments for CIVIC?
Yeah, so when we're looking at, in particular, the safety case and developing and validating the safety case, it is incredibly necessary to be able to measure the amount of risk that is present in the machine so that we can look at areas to improve, as well as ensuring that the system as a whole is safe. And so one way that we can do that is through something with frequency, completion, as well as severity. And so essentially, when we're looking at frequency, frequency is what is the rate at which something is present, like a hazard. So for example, we see those humans in the field with the red boxes around them. How often are people going to be surrounding the tractor or vehicle of interest? So then once we've looked at the frequency of the situation, then we might look at the completion. And the completion might be related to, given that there are people there, what is the likelihood that we won't be able to avoid the situation? So for example, in order to avoid the situation, the system might be able to avoid it itself, or the people might be knowledgeable enough to realize that they're in a dangerous situation and remove themselves from the situation. And then finally, when we're looking at severity, we're looking at what are the consequences of a potential hazardous situation. So in this case, the vehicle might be smaller than a tractor or a combine, and so the injury might be less. So it might only range from like a broken arm as opposed to, in the case of a combine, a death. And so in particular, when we're looking at high frequency situations, we want to make sure that the completion is very, very low so that there's not as many situations in which a bad outcome arises. Next slide, Alex. So when we look at the tools that we might use to mitigate these issues, we need to have perception and detection of these risks. And so one thing that is becoming more common throughout autonomy is using AI and other image processing like solutions. And so when we're looking at this, oftentimes when we train AI models, they're dependent on the quality of the input, like the training set. And so if the training set is only of perfect, clear images, then we might not get like the level of performance or reliability that we want, because the camera might be in a bad state, like relative to what we expected it to be or what we trained it off of. And so when we're looking at ensuring that our sensors are actually performing the way that we want them to, we need to be subjecting them to the like situations that they'll be subjected to in the real world. So in this case, for example, snow, rain, or fog might impact the quality of the image, that might impact its ability to detect people. And so, as mentioned in the corrective action section of this slide, you need to essentially test your product or test your technology in the situations that like it'll actually be in. And then if you notice that the performance is not as good as you want it to be, then you will need to retrain it or retest or ensure that you're incorporating those unforeseen circumstances. Is there anything else
Dave,
you'd like to add, Alex?
No, I just to show that, of course, this is a simulated, but what we did is to just to illustrate what Dave was just mentioning. The previous slide shows a very neated image where the detections are very reliable for the 3 people there. But let's say that when we actually pollute the image using the images, now the detection becomes weak. And then when we have a weak detection, then we know that we have a problem. And as Dave was discussing earlier, especially when we're talking about kids that may not be as aware of the dangers that a machine may have in the field, it becomes critical that the detection of children is very robust. So in this case, as Dave was explaining, we would look at this and promote the retraining of the neural network using more images with children so that we develop a more robust detection in this case. Maybe this is a good point to make a pause, Leonardo and Rachel, and I saw that there's a few questions on the YouTube chat. Do you want us to field some of those?
Yeah, I think we can. That sounds good.
I think Leo's going to read off the questions, or did you already read them, Alex? You can dive in directly if you'd like.
Oh, okay. So yeah, I'm reading. So there is, for example, the first one was from Promine Scalabrini. Can the safety research being done for autonomous vehicles be directly applied to safety in agriculture? The answer is almost. And I think that the approaches, the structure, the tools, the methodologies are applicable. What may happen at times is that the type of environment, the environment around an agricultural operation tends to be very different from streets and bystanders and signs, etc. So then in other vehicles and the density of the vehicles, etc. So sometimes what we have found is that there has to be an adaptation of the tools, but certainly the underlying research is very, very relevant. And I would invite we at Balance are looking for maturing tools that would allow us to do things like assess a neural network detection so that we can establish that that is acceptably safe. Then the next one, it says from Jonathan Felipe, how long does it usually take to begin the research to production, to begin the research to production in agriculture? because it's a setting with less people, I believe it might be easier to experiment with new things. Am I right? The answer is yes. As it was presented in the, and I'm going to go back to the slide, as I was discussed by Dave, the risk profile is very different. On the left, we have very cluttered, mostly very cluttered highways or streets with a lot of traffic and with unpredictable driving patterns by other drivers. On the right side, typically the environment is dedicated to the particular operation. If we're going to be harvesting, most likely there will be a few vehicles that are focused on harvesting, and each one of the drivers is going to drive a fairly predictable pattern that is defined by the job at hand. So this is my opinion. I think that we're going to see robotics at scale be delivered and deployed and commercialized in agriculture and other off-road applications. Another example is mining, even prior to broad adoption of autonomy in automotive. The next one is Melby Lau. Hi, Alex. Thanks for the talk. Yesterday, we had a presentation about robotics in mining, and the presenter said that the hardware robustness is a big deal in that context. Does the same thing hold here? Dave, do you want to take that question?
Sorry, could you repeat? I think I kind of heard like some noise in the background.
Yes. Yesterday, we had a presentation about robotics in mining, and the presenter said that hardware robustness is a big deal in that context. Does the same thing hold here?
So I think hardware robustness is definitely important. Like, for example, when we're looking at sub modules, like if we're looking at, for example, a sensor system, we want to make sure that the sensor system that we're using is actually robust and working the way that we want it to, in order to be able to incorporate those outputs of the sensors into our model. But in general, as Alex has mentioned before, especially in autonomy, we've noticed that software is a particular area of concern for manufacturers and developers.
And I will add to what Dave said that yes, of course, the robustness of everything hardware is critical, but the tools to assess safety of mechanical, hydraulic, electrical, electronic systems exist. The tools to assess the safety of software are fairly mature. There's still opportunities to improve, but the tools to assess whether a module, let's say a neural network that doesn't have really code or models, but instead has a large number of nodes with numbers, even if we had an army of people examining a neural network, we would not be able to tell if it is safe or not. That's why we're looking towards the research community in artificial intelligence to not only continue developing the AI, but also the tools to evaluate the AI, in this case, from a safety perspective. There's another question from Enzo Paranawa. Hello, Alex. Where do you see your research headed in the next 5 to 7 years? Enzo, I would not say that we're doing research. Balanced Engineering is a company that is taking advanced tools and applying them and helping startups and very large companies to move technology to product and eventually to growing businesses. So we are mostly in the application, in improving process, training, tools, and methodologies to help companies bring successfully research and development into products and eventually to be successful in the marketplace. Where is it heading in the 5 to 7 years? I think that we're going to see a tremendous explosion of more and more capable AI, and we will need to have significantly better standards, best practices, and tools in order to assess those and to be able to guarantee or certify or prove that our machines in the future with all of this artificial intelligence are indeed safe. We have put some of these thoughts in a number of publications. For example, SAE, the Society of Automotive Engineers International, publishes the series of SAE Edge reports. Here you have a couple. There are more coming that I would be happy to point if anyone is curious. Like, for example, unsettled topics in obstacle detection for autonomous agricultural vehicles. There's also unsettled issues regarding the commercialization. And we have been helping to author those reports to bring some of the topics that we have discussed today into these publications. In addition to that, if you are interested in knowing more about new trends in AgTech, the benefits of automation, functional safety, building safe equipment, etc., you may want to visit our blog at Balance Engineering, where we have been starting to write articles related to these topics, like, for example, maximizing the productivity in agriculture with safe and secure machines. The link is there below. Leonardo and Rachel, there are more questions coming. Do you want me to continue fielding them?
I think we can maybe finish the presentation and then cover the next questions.
Okay, very good. So let me get to the conclusions. First of all, autonomy in off-road applications is being commercialized. As I showed you at the beginning with this advertisement, here's the list of robots that you can actually buy. Technology is evolving fast, enabling great capabilities. However, standards, documented best practices, industry practices, etc., are lagging the technology. That is the case that I just mentioned with neural networks. Standards and tools to integrate AI modules is needed in the field of field robotics or off-road autonomy. And also, I would like to send a message to all you early career professionals or students. You can strongly differentiate yourself from other professionals if, in addition to knowing some technical area in depth, you also have safety experience. So I strongly recommend you, and for example, that is what Dave, my co-presenter, is doing. He is studying architecture and many other things in the School of Engineering and Computer. Oh my goodness. Dave, ECE stands for Electronic and Computer Engineering. That is what it is. Sorry. So
electrical.
He is electrical. Thank you. My apologies. So he is working with us so that he can continue to develop his technical expertise, but also get familiar with standards, practices, etc., because the professionals that in the future are going to be technically savvy, but in addition will have this focus on safety, are going to have significant demand. I can tell you because today, our customers, our clients that go all the way from startups like the Burrow robot, all the way to the larger companies like John Deere, Case New Holland, and ACO, they're not able to hire all of the safety engineers that they need. And finally, safety shouldn't be thought as a problem or as an obstacle. Done well, early safety focus encourages optimal design practices. So even if you're working in a lab prototype, it is never too early to start thinking and asking yourself, what are the potential risks? We're going to write them down. And every time we do a respin or rewrite of software, we're going to try to make our software continuously safer. That safety culture is what Dave referred to when he said that the enterprise is trustworthy. I don't want to get into any details, but for an example, we know that today, Cruise, as a subsidiary of GM, is having some challenges to deploy their robotaxi fleet in San Francisco and other cities. So the topic of safety should be thought out from the beginning in a very transparent way, following best industry practices and in a documented way. Leonardo, that was the end of our presentation.
Awesome, Alex. Thank you very much for the presentation and for the awesome work. Um, we'll now cover the remaining questions in the chat. So, if you allow me to start with my question is, so you presented some, you mentioned some safety standards. So I was thinking, like, do you think that for, and when we talk about research students interested in doing research in robotics for agriculture, or when proposing new projects or thinking about new pathways, do you think it's it's useful to think about these standards, get familiar with them, and consider them from the beginning, or there is value in let just your mind fly, and then in the end you try to adapt your solution to be according to these standards?
Very good question, Leonardo. Uh, the reason I wanted to provide you with a few examples at the beginning that failed and we had to go back is because we didn't do that. Even if you know that you're going to be building a system that is going to be intended to show a capability in the field where people are around, if nothing else, you don't need to become an expert in the safety standards for agriculture, but you need to at least be aware of them and be aware of the initial part of those standards that has to do with the risk assessment. If you execute a risk assessment for your prototypes, you will know where are the weak areas, and you're going to be able to bring expertise to see how we can fix that. But if you try to develop the functionality and at the end you will say, okay, how do we make this safe? You may find that your architecture needs to be redesigned with a lot of cost and time in order for it to be safe. So my recommendation, you don't need to put everything at the beginning, but make sure that at least you do the risk assessment.
Okay, great, thank you. So we'll now start answering the remaining questions in the chat. So Caio Conti asked, "Hello, Alex. Greetings from Brazil. The whole political economic context here is not as favorable for entrepreneurs as in the US. So do you see many business opportunities in AG here regardless?"
Caio, boa tarde. Yes, the answer is absolutely. In fact, Balance Engineering has a team in Brazil because I'm convinced that Brazil presents tremendous opportunities for ag automation. Ag is maybe, depending on the way you count the numbers, maybe a fourth or a third of the PIB, the internal product, I mean, the economy. And agriculture continues to be a fundamental element of the economy, and it's a fundamental element of innovation. If you want to write to me, I can point you to a few places like Active Garage in Piracicaba and many other hubs where the innovators are getting together, and I am convinced that there will be a lot of great opportunities. Talk to me.
Great, awesome. Yeah, thank you. So the following question, Ana Paula asked, what are the things you're looking for in people that want to work with you? Which skills are important to focus on?
Of course, technical skills, but I would say that for anything that we have discussed today, having a sound systems engineering approach is very important. You need to understand aspects related to customer needs, to requirements, to functional architecture, etc. Because of all of these concepts are very supported by sound systems engineering. So that is one side. So you can be a great mechanical person, but you need to know how these things come together using systems engineering. And on the more soft skills, I want you to be able to communicate, to be proactive, to be able to present well, to be curious, and always to be willing to challenge and to provide new ideas. Languages are important too.
Great, that sounds great. Thank you for the answer. So following question. So Jailson Johnson asked, building on top of the overlap between mining and agriculture, a major problem of deployment robots in mining in yesterday's talk, was training the people to use them. Is this something you have to deal with as well?
Oh, Jelson, it is almost that I asked you to ask me a question. The reason I say that is because in ag, training is also a key opportunity for business, but also a tremendous need. In fact, one of my investments, a startup in Brazil, is focused on training operators and technicians in Brazil because of how much training is needed to diagnose, maintain, fix equipment, and also to operate equipment optimally. So it is a similar situation in terms of training, except that in ag is even more critical.
Okay, awesome. So next question. Davi Santiago asked, how is your research accepted within the agricultural area? Do you believe that there will be a large replacement of the existing human workforce with the research product?
Okay, this is a really important question because we're always dealing with this idea that maybe robotics is going to take a lot of jobs, etc. I'm going to give you an example. In Brazil, sugarcane harvesting went from 5% mechanized to 95% mechanized in about 20 years, letting hundreds of thousands of people that were doing one of the hardest jobs to actually move on to better jobs, whether it's operating equipment or doing some other things. The key thing to keep in mind is that in the developed world, the US, for example, to some extent, areas of highly mechanized agriculture like Brazil and other countries in Latin America, Europe and others, the amount of workforce that is working in agriculture to produce food is very small compared to the complete population. A couple centuries back, more than 50% of the people were actually focused to producing food for humanity. But in these markets that I just described, it's just 1 or 2% of people who are working. So the answer is yes. Farmers are lacking labor. Most labor likes to live in the cities, and farmers have no help to actually produce food. They're welcoming the robots.
Okay, great. Thank you again. So now one question that's more for like guidance for um, the students watching the talk. What did you not learn during your PhD that you wish you had on the technical side, on the soft skills side, or other skill or any experience?
I think that one is, as I mentioned, I wish that I had more formal systems engineering. Sorry, Claudia had a message there.
Oh, I apologize.
Claudia?
I need to go. Yeah, thank you. I apologize. I need to go, but I just wanted to, thank you again for the invitation, and I'm looking forward to learning more about robotics and all those projects you're working on and how they're helping improving our lives.
Very good. I will ask Rachel to give me your contact, and I'll reach out to you,
Perfect.
Claudia.
Thank you. Oh, that would be
Te
a
llamo y
pleasure.
conversemos, ¿ya? Conversemos un
Claro,
poquito.
genial. Muchas gracias.
Bien.
Muchas gracias a todos.
Here.
Chao.
Thank you.
Sorry, Leonardo, I was answering your question and I forgot the question.
No,
No, I know. So I was talking about systems engineering and what I did learn, right? I wish that there would be, but I have to say that Carnegie Mellon has improved significantly because now you have the two master programs, right? And one of the masters is in research, but the other one is in system development. And I know that people like Dimi Apostolopoulos and Parag Batavia and John and others are, doubling down on systems engineering, and that is a really good thing.
Oh, great. Yeah. So if you're interested, you now are aware of one opportunity at CMU. And well, since it's already 1 p.m. in Pittsburgh, I think we might have to end up the session, or we have a couple more, one or two more questions if you want to keep going.
A couple more minutes, yes.
Okay, um, so one more is, oh, what do you wish that you had known at the beginning of your academic journey? So before your PhD, building on top of the previous one.
Better English.
Sorry.
It was
Oh, English.
English. That is what I said. Languages are good. Try to learn them as early as possible, because in my transition from undergrad to graduate, I struggled quite a bit at the beginning with the English, and so that is one thing that I would strongly recommend. Try to learn different languages early on. The other one, perhaps, is that maybe I didn't come with the appropriate level of mental structure in how to do things in a more organized way. I think that I had to learn that significantly more through the graduate program.
Okay. Oh, that's good advice. Thank you. The other two questions were actually covered already. Were
Okay,
more about which skills to build. We already covered them. So, well, I want to thank you for joining us today, you and Dave. Thank you for the presentation. And do you have a few more words to say before wrap up?
thank Dave. Anything?
No, just thank you for having us.
Well, of course, my
Yes.
pleasure.
Thank you for having us. And the topic of off-road autonomy is fascinating. There's lots of work to do, and the topic of safety in autonomy is fundamental for business success. So get connected, talk to us. We'll be happy to help you if you are interested. And thank you.
Thank you very much. Thank you for everyone who joined, and hope to see you in the next session. Bye bye. Have a nice day.
Thank you. Bye.
Bye. Okay,